Hello and welcome to another episode of the book club. Today we are going to be continuing where we left off. We finished up that section about the integers, T's complement and all that, and I think we really developed a strong intuition for that stuff, and yeah, so I believe it's time to move on to the next section. I believe that's 2.5. Let me get out the book and we'll get right into it. All right. Let me see here. So we finished 2.4, signed and unsigned numbers, and we're going to be reading 2.5, representing instructions in the computer. We are now ready to explain the difference between the way humans instruct computers and the way computers see instructions. Instructions are kept in the computer as a series of high and low electronic signals and may be represented as numbers. In fact, each piece of an instruction can be considered as an individual number, and placing these numbers side by side forms the instruction. The 32 registers of RISC-V are just referred to by their number from 0 to 31. And we have an example here. It says translating a RISC-V assembly instruction into a machine instruction. It says here, let's do the next step in the refinement of the RISC-V language as an example. We'll show the real RISC-V language version of the instruction represented symbolically as add x9, x20, x21, first as a combination of decimal numbers and then of binary numbers. So the decimal representation is 0, 21, 20, 0, 9, 51. So I'll draw it out because they did it as like a diagram. So let me see here. Whoops. Oh, I'm in mouse mode. All right. So let's just go down here. And we're going to say we are doing add. Here, let me move some of the stuff on my desk. It's a bit crowded here right now. All right. X9, X20, X21, and of course, if you watch my Risky Business episodes, we've already covered the instruction encoding for the base ISA, and Pair has covered it in bitwise, of course, as well. So this is, if you follow those, either what I do on Risky Business or bitwise or anything like that, the stuff in this section should just be review. It shouldn't be anything too surprising. But if you don't, this might be your first introduction to how these instructions actually get encoded. So they're starting out showing us just the decimal numbers, which in my opinion is not very useful, but that's what they're doing, so we're going to write it out. So they show 0, 21, 20, 0, 9, 51. So it's just a little diagram like that. This is represented in the machine sort of like that, except that what you're looking at here are decimal numbers, and of course it's actually stored in binary. So let's take a look here. At the next page, it says each of these segments of an instruction is called a field. The first, fourth, and sixth fields, containing 0, 0, and 51 in this case, collectively tell the RISC-V computer that this instruction performs addition. The second field gives the number of the register that is the second source operand of the addition operation, 21 for x21, and the third field gives the other source operand for the addition, 20 for x20. The fifth field contains the number of the register that is to receive the sum, 9 for x9. Thus, this instruction adds register x20 to register x21 and places the sum in register x9. So you can see what they're talking about here is that this, and this translates to add. This translates to register x21, this to register x20, and then this one here is register x9. So that's saying add x9, x20, x21. So take x20 and x21, add them together, store them in x9, and this is, you know, how it is actually represented in the machine, but written as decimal. And if you take a look here, let me peruse around a little bit here. This will be easier actually with the mouse, so I'm gonna turn my mouse on. Oh wait, never mind, it's right here. Okay, so yeah, we have these different types of instruction encodings, and you can see here that they have different fields. If we look here, we have one right here, the R type, which is, it has a funct7, an RS2, an RS1, a funct3, an RD, and an opcode, right? So that's what we're doing here is, you noticed how I circled like one on the leftmost and then like one over here and then one over here, those three decimal numbers, and I said those three are an add. Well, that's because they're the opcode field, the funct3 field, and the funct7 field of the R-type instruction encoding. And then we said that you had your destination register over here, right? So that's the RD, that's the registered destination, right? And then you had the X20 over here and the X21 over here. Well, that's the source 1 and the source 2, register source 1, register source 2, right? So that's what this actually is. So what we have is 7 bits are going to be the funct7, 5 bits are going to be the RS2, 5 bits are going to be the RS1, 3 bits are going to be the funct3, 5 bits are going to be the RD, and then 7 bits are going to be the opcode, and that gives you in total a 32-bit instruction. So that's how that works. So it's, you know, it's binary, it's just a 32-bit integer, and, you know, it's split up into those fields, and that's how those fields are, you know, encoded to represent something like an add. So if we go back over here, where were we? Over here. So that's what we're working with. Not too complicated stuff. And I believe next is going to talk about the representation in binary. Yeah, so each of these segments of an instruction is called a field, blah, blah, blah. The second field gives the number of the oh yeah, we read that. The instruction can also be represented as fields of binary numbers instead of decimal. So yeah, they're going to show that now. So they write out 7 zeros. Right? And that's the 0 up here. And then we have 5 bits, which is 10101. And then we have 10100. And then we have 000. And then we have 0, 1, 0, 0, 1. And then finally, and I'm going to need to move this a bit so it all fits on screen here. So finally we have 0, 1, 1, 0, 0, 1, 1, right? So these are, you know, this is the same exact thing that we just took a look at, that we just drew up here, just in binary this time. And so of course, you know, this is a 7-bit number. This one's 5-bit. You know, 5, 3, 5, 7, right? So this is specifically this. So, and that corresponds with what I just showed you a little bit ago of what we had done on Risky Business of looking at the instruction encoding. That's an R-type instruction. And I showed you how it was 7 bits, 5 bits, 5 bits, 3 bits, 5 bits, 7 bits, you know, and like I say, this was the funct 7, this was the, and the 7 means 7-bit, right? This one was the RS2, then you have the RS1, then you have the funct 3, that's 3 bits, and then, you know, you have the destination register, and finally you have the opcode, right? And I should say, you know, this is low, this is high, right? Just to be clear. So most significant bit on the left in this drawing, least significant bit on the right. This layout of the instruction is called the instruction format. As you can see from counting the number of bits, this RISC-V instruction takes exactly 32 bits. A word or 1/2 of a double word. In keeping with our design principle that simplicity favors regularity, RISC-V instructions are all 32 bits long. This is a bit of an oversimplification in that RISC-V actually has an extension called the compressed extension, and I believe it's actually like required now or something. Don't quote me on that, but I remember seeing a thing about someone complaining about a change to the standard involving compressed extensions, like making them a required part of the standard. Maybe for like, you know how there's the G extension, which is, you know, it's I think it's IMAFD. So integer instructions, multiplication extension, atomic extension, floating point, and double precision floating point. All of those instructions is kind of the general purpose instruction set. And I think maybe they either made C required to go along with G, or maybe it's like, I don't know the specifics, but there was some discussion relating to that. So I'm not sure the status of the C extension in terms of how, you know, required it is. But for example, you know, the high 5 unleashed up there, of course, has compressed instructions, and I believe the high 5 1 has compressed instructions as well. The high 5 1 was, I think it was IMAC. So no floating point hardware, but I believe it had integer, the base ISA, multiplication, atomics, and the compressed instructions. So the thing with compressed instructions is that the idea is that you can take, some common instructions that you would have, and instead of encoding them in a full 32-bit integer, it could be useful to save space to encode those common sequences in like 16 bits. And I believe it's a 16-bit encoding for the compressed instructions. So in practice, you're pretty much always going to be using the compressed instructions whenever you can. It's not like there's a performance penalty or whatever. It's it just is a more efficient encoding for common sequences. And so it's not actually true that RISC-V is only 32-bit instructions, like the base ISA is only 32-bit instructions, but in practice you have 32 and 16-bit instructions, where lots of common stuff is done in 16-bit to keep things compact and be able to fit more instructions in the iCache and things like that. It's just a nice way to go. So they're oversimplifying. I just want to point that out, that they are oversimplifying in this book when they say RISC-V instructions are all 32-bit. It's the normal and uncompressed instructions that are all 32-bit. But there are 16-bit compressed instructions, so you should be aware of that. Let's see here. To distinguish it from assembly language, we call the numeric version of instructions machine language, and a sequence of such instructions machine code. And that's an important distinction that you should be aware of too, that assembly language is like when we write out instructions like this, you might think of that as being talking directly to the machine, but really the machine just understands the the numbers, right? And that's called machine code. The raw numbers are machine code, right? And the the language that you're typing up here that directly corresponds to the machine instructions, this is assembly language, and it needs to be assembled down to machine code. And so one of the things I've talked about doing on my series, not on the main series, but just as kind of like a side project for myself, is I want to do some coding on the high 5 unleashed up there, where I just literally type into a hex editor programs directly in machine code. And I think that would be very useful for myself to develop a lot of familiarity and being more comfortable with the actual representations of instructions, because it's useful if you are doing very low level stuff and you want to pop open something in a hex editor and just peruse through it and be able to say, oh, I recognize common instruction sequences in this hex wall of hex. And that's useful for debugging if you're writing like an assembler or something like that to translate assembly code to machine code. It's nice if you can be able to eyeball the output and say that doesn't look right, like that's not the instruction I'm expecting it to output. So that's something that I personally want to do, but I believe many people would not want to go so far as practicing typing machine code directly. But yeah, that's just an important distinction to make, the difference between assembly and machine code. So let's continue reading here. On the side, it has a few things, so I'm going to look over this right now, the margin, It's has some definitions for us. Instruction format, a form of representation of an instruction composed of fields of binary numbers. Machine language, binary representation used for communication within a computer system. And then hexadecimal, which we haven't got to in the text here yet, but it's numbers in base 16. And I've kind of sort of assumed you understand hexadecimal if you're following this me reading through this book, but it looks like they actually cover hexadecimal here. So maybe I kind of jumped the gun, breaking out the hexadecimal. Like in the last episode, I did some examples that I numbered the actual representations in hexadecimal because it was convenient for me. But yeah, so we're gonna actually properly cover hexadecimal today, I guess. So I'm sorry if anyone watches this and got confused by that because they haven't been exposed to hex yet. But yeah. So anyway, it would appear that you would now be reading and writing long, tiresome strings of binary numbers. We avoid that tedium by using a higher base than binary that converts easily into binary. Since almost all computer data sizes are multiples of 4, hexadecimal, which is base 16, numbers are popular. As base 16 is a power of 2, we can trivially convert by replacing each group of 4 binary digits by a single hexadecimal digit and vice versa. Figure 2.4 converts between hexadecimal and binary. So yeah, hexadecimal is a very simple concept. Just like, in decimal, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now we ran out of symbols, right? There's only 10 symbols. So to get the next number, what you do is, you go 1, 0. So the ones place drops back down to 0. It wraps around, right? It wraps back around to 0. But then the next digit gets incremented up to 1, right? And similarly in binary, you have 0, and then you have 1, and then you're out of digits, so you need to set the low digit back to 0. It wraps around again, but then the high digit gets set to 1. So I'm just gonna underline these to indicate that these are a single number, to make that clear. But yeah, so this is a number, this is a number, and then the next one goes to 10 because you've used up all your symbols. It works the exact same way in hexadecimal. You can do this in literally any base. It's just that if you go higher than 10, you need more symbols than than what you have in decimal. So what symbols do you use for hexadecimal, right? And so what you do is you just count up like this: 7, 8, 9. But then after 9, like I say, we need new symbols. So what are we going to use? Well, the obvious thing is let's just use letters from the alphabet, right? There's a bunch of symbols we haven't used yet. So, A, B, C, D, E, F. And then after that, it wraps around to 10. So again, this is just, if you count this, like this span right here has 10 unique digits. This one has 2 unique digits. This has 16 unique digits, right? So you have the usual 10 here, but then these bad boys over here give you an extra 6. So it's just another base. It's just another number system. It's base 16 instead of base 2 or base 10. And the reason it's useful is because if you take binary, so let's just take this number right here, the one we were just looking at. It's 0, 0, 0, 0, and then 0, 0, 0, and I'm gonna write it like this. So 0, 1, 0, and then 1, and then we have 1, 0, 1, 0. We have a 0. Yeah, 0, 1, 0, 0. And you have 1, 0, 1, 1, and then 0, 0, 1, 1. So what I've done here is you'll notice I spaced it in groups of 4. And the reason this is useful is because what we have here are, groups of 4 binary digits, and a group of 4 binary digits is called a nibble. A group of 8 is a byte. And so what we've done is we've grouped this 32-bit number into nibbles. And the reason that's useful is because, see, the reason hexadecimal is useful is because 16 is a power of 2, right? It divides evenly into binary numbers. So, when you have 2 to the 4th, you have 16 different combinations, right? So 4 binary digits can represent 16 different numbers. And and again, you can check that on your fingers easily if you watched the previous episodes and understand counting in binary. That's trivial to check that there are 16 different combinations of four digits in binary. While in hexadecimal, a single digit has 16 different possible values, right? So it corresponds, every hexadecimal digit corresponds to 4 binary digits. So it's a much more compact representation, and it's very trivial to convert between binary and hexadecimal or hexadecimal and binary. That's a very trivial conversion to do. So it's a very convenient number system. Whereas in base 10, if you want to have 10 different combinations, well, you can just count it off on your fingers, right? You have, this is your first combination, then 2, 3, 4, 5, 6, 7, 8, 9, 10. Kind of awkward here. So you've used like these 4 fingers, right? So you've used 4 digits, but then you have a bunch of unused symbols, right? This one, this one, this one, this one. Like, you've got a bunch of stuff that you haven't used. So decimal does not split cleanly into binary. It's like if you wanted to split binary into groups of like decimal, if you follow what I'm saying, I don't know how to word that cleanly, but if you split it up, it's like between 3 and 4 digits. Somewhere between 3 and 4 binary digits corresponds to a single decimal digit. It doesn't divide evenly, right? So that's really messy. And as a result, the conversion between decimal and binary is pretty ugly. Hello, Kroiva. Thank you for tuning in. So with hexadecimal, it's a lot cleaner. So, if you have a number like this, you've got, 0, and then 1, and then what do we have here? 5. Was that right? That looks right to me. What do we have here? I believe that's 9, 0, and then this would be 4, and then this would be 11, so that's going to be B, and then That's just going to be 3, right? So this long number here could be written much more concisely as just 0, 0x, and that's just the way in like C and other programming languages that we represent a hexadecimal number is you just lead it with a 0x. If you've seen like HTML color codes, they usually just use like a pound sign or a hash mark for leading off a hexadecimal number. But basically it would just be 0, 1, 5, 9, 0, 4, B, 3, right? And that's our hexadecimal number. So that's kind of how that works. And yeah, it's a very simple conversion. If we just write out the table here, that's easy enough to do. So let me put that up here. So we're just going to write out all of the different patterns. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and of course the highest number you can represent is 15. Those correspond to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Whereas again, if you were to do this in decimal, it doesn't split cleanly. So what you have is these ones stay the same, but you run into a problem once you get to 10 here. So now you need multiple digits. And you end up with something like this. So the hexadecimal is a much cleaner representation here, where each group of 4 corresponds cleanly to a single digit, unlike decimal where it's either 1 digit or 2 digits depending on how big the number is. And that's particularly nasty because it means if you have groups of 4 digits, a big number that has groups, you break up into groups of 4 digits, because it doesn't split cleanly, what's going to happen is, when you have a number like F here, right, you have 15, and so what happens is if you have a number like FF in hexadecimal, and then you want to say, well, what's that number in binary? Well, F is just all ones. It's just a group of 4 ones. So it's trivial to do that conversion, right? But now if you want to do decimal, right, like what is this number going the other direction? If you have all ones, what is this number going to be in decimal? Well, you can't just say like, okay, well, this group is 15 and this group is 15, right? This is not how this works, right? It's Croefa says, unrelated, I am of the opinion that humans should have adopted the dozenal base 12 system instead of base 10. I mentioned the dozenal system in I believe the previous book club episode, day 18, and talked about some of its benefits. how many numbers divide more cleanly into nice fractions, and how that can be useful for something like a carpenter working with like feet and inches and things like that, and you know, our time and things like that. But I would not say I'm an advocate of dozenal myself, actually. But I definitely would not deny that it doesn't have its benefits, and I would also agree that base 10 is not so much the natural system because we have 10 fingers like everyone says. I don't think that's a sound argument, and humans have definitely used different bases for a number of different things and across different cultures throughout the ages, and it's not really that decimal is the, you know, obvious thing. And there are definitely benefits to using different bases as well. But anyway, you know, this is wrong, right? Like, the actual number is 255, and of course the way you need to get that is you need to actually look at the value in each place and do the summation. So you know, you need to say like 2 to the 0 plus 2 to the 1 plus, you know, for each of these digits to get the 255, because these are not, this doesn't split cleanly, so it's like carrying over into the next place over, and yeah, it's just it's not a clean representation. Whereas with hexadecimal, you can just say, you can literally say FF and it just works, right? Because there's no spilling over to the next place or anything like that. You can just grab groups of 4 digits and directly translate them, and that works because it divides evenly into the base 2. Yeah, I mentioned that as well, the idea of counting with the knuckles. Personally, I don't see that as a good counting method, although I've never, you know, practiced it or anything. But to me, it feels like it would be awkward to try to count on the knuckles. It doesn't seem nearly as good as using a digit as a digit, you know, 1 or a 0 to me. I think it's much more natural counting on your hand in binary because, you know, the finger is up, it's a 1, the finger is down, it's a 0, and, you know, it's a digit. Like, we call our fingers digits, right? And we call these, you know, numbers digits, right? And a finger corresponds, as a digit, corresponds very cleanly to a binary digit. I really kind of find that pleasing. Whereas using the knuckles is a little bit hairier, in my opinion. But anyway, let's continue on here with the book. So yeah, you should have, from what I've shown here, you should have a good understanding of hexadecimal now. If you watch the previous computer organization and design episodes, I covered kind of how bases work in a general sense, since the book was covering that as well. And all of that intuition applies directly to base 12 as well, of course. So I don't know if I can find that stuff here, but yeah, I might not be able to show that stuff right here, but yeah, I'll refer you to the previous episodes if you want to see more of working with different bases. Let's see what the book has to say. Where are we? Okay, so they have a chart of hexadecimal and binary. So they did the same thing I just did, where I showed you, I listed out the the binary representations of nibbles and the hexadecimal representation and the decimal. They just show the hexadecimal and the binary representations in a table. So yeah, that's figure 2.4. I'm just going to skip over that. I'm not going to draw it out the way they drew it. They organized it differently, but it's the same thing that I drew. So you're not missing anything. It says the hexadecimal binary conversion table. Just replace one hexadecimal digit by the corresponding 4 binary digits and vice versa. If the length of the binary number is not a multiple of 4, go from right to left. All right, because we frequently deal with different number bases, and that's another thing I should say, when I wrote out, just as a side note, when I wrote out this number as this number, I went from left to right, but I did that because I know this is a 32-bit number, so it divides evenly into nibbles. What they're saying is, you know, if the number does not divide evenly into nibbles, you need to start at the right and work left, right? Because this is the least significant bit. You start from the least significant bit and work towards the most significant bit when you're splitting them up into nibbles. I just wrote it this way when I did this example because I knew this was a 32-bit number which splits nicely into nibbles, and you write normally left to right, so it was just natural to do that. But that is an important point to point out, that you should be working right to left, you know, from the least significant bit to the most significant bit, because if it isn't a nice multiple of 4, then you're going to run into issues, right? You're not going to get the right number if it doesn't divide evenly into groups of 4. So that's important to keep in mind too. So let's see here. Because we frequently deal with different number bases, to avoid confusion, we will subscript decimal numbers with 10, binary numbers with 2, and hexadecimal numbers with hex. And again, we talked about the subscripting in the book before, that's how they do this. And we, when I draw examples out, I'm generally assuming it's understood from the context. I'm usually not being too precise about whether a number is binary or decimal or hexadecimal or whatever. It's just kind of assumed that you know what's going on. But in the book, they're more explicit about making that clear. So if you do have trouble following along with my my whiteboarding, consider getting a copy of the book, because they're much more explicit about this. And they say if there is no subscript, the default base is 10. By the way, C and Java use the notation 0x NNNN for hexadecimal numbers, and that's what I showed you too. I mentioned that 0x is the common way we prefix a hexadecimal number, and I also mentioned that HTML codes use the little hash or pound sign for a hexadecimal number when they do color codes, which is pretty common to see. And then we have an example here, binary to hexadecimal and back. Convert the following 8-digit hexadecimal and 32-bit binary numbers into the other base. So ECA86420 in hex, and then for binary, 0001, 0011, 0101, 0111, 1001, 1011, 1101, 1111. So those are 2 numbers, and they want us to do the conversion for each of them between binary and hexadecimal. So let me write out the hexadecimal number first. So it was ECA86420. ECA86420. So it's pretty straightforward to do this. First of all, the any of the decimal numbers are just going to be decimal. So 0, 0, 0, 0. I'm just going to do the ones that are decimal first because that's the most intuitive, right? And then the 2 is going to be 0, 0, 1, 0. The 4 is going to be 0, 0, 1, or sorry, 0, 1, 0, 0. And then the 6 is going to be 0, 1, 1, 0, right? Because 4 plus 2 is 6. So that's the 6420. And then the ECA86, I'm gonna, or sorry, ECA8, I'm gonna write it below what I just did, but this is the least, the low end, and then this is the what I'm going to write down here is the high end. I should have put the high end above this, but I didn't leave space for it, so I'm just going to write it down here. So 8 is obviously just going to be this, and then A is going to be 10, right? So if you have 8 here, then you add 2 to it, that's going to give you 10, right? So it's going to be 1, 0, 1, 0. And then C, if you just add 2 to what we just did, of course, that's going to get you to C. And then E, again, if you just add 2 to it from C, so that would just be 1, 1, 1, 0, right? So there you go. So let me just move the lower bits onto this line. Right, so let me just cross this one out. So yeah, this would be this in binary. And then let's take, see you later, Croifa. Take care as well. And thank you for tuning in. So now we're going to do some binary. So we're going to have 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. All right, I think that's what they had in the question. Just double checking. Yeah, I believe that's right. So we're going to start translating this to hex. And again, it's pretty easy. This is just going to be 1. This is going to be 3, 5. And then let's see here. We've got 7, because this would be 8 over here, so that's 7. That's going to be 9. Let's see here. So that would be B, right? Because 8, 9, 10, 11. So B. And then 8, let's see, 9, 10, 11, 12, 13. So if A is 10, B is 11, C is 12, D is 13. So that would just be D, and then this would be F, right? Yeah, that looks right. So the number would be 0x1357 9B D F. And again, see how easy this is to do these conversions, right? These are 32-bit numbers that we're working with here, and we're able to do the conversion in our head, right? Like, it's pretty simple to do that math in our head to convert these, right? And if you imagine converting a 32-bit binary number to decimal, that would be a lot more painful. You'd be breaking out the calculator, right? So if you didn't already practice some binary to decimal conversions and so on and so forth, I think they suggested doing some of that in the previous section, or one of the previous sections of chapter 2, where they were showing, you know, kind of introducing binary and decimal and converting between them. I'm pretty sure they did some of that. So, you know, if you've done some of that, you'll know that it's not clean. It's not easy to do that conversion. You need to do some actual math, some actual annoying, tedious calculations. Whereas with hexadecimal, it's so simple that you could do it in your head. So that's kind of the reason we like hexadecimal. And when we're programming, you'll see we use hexadecimal a lot. It's pretty common to use hexadecimal in programs. So let's continue looking here. They say using figure 2.4, the answer is just a table lookup one way. So they say the answer for the hexadecimal to binary should be 1. Let me just show you 1 1 1 0 1 1 0 0 1 0 1 0 1 0 0 0 0 1 1 0 0 1 0 0 0 0 1 0 0 0 0 0. So yeah, we got that right. And like I say, you know, you didn't see me do any math really, other than maybe counting a little bit out loud to myself. You know, it's basically, you can do this in your head, especially if you memorize the binary and hexadecimal pairings. Then this is like instant to do this. If you memorize that, and it's easy to memorize because it's just like 16 different patterns you need to remember, right? I don't have them memorized, as you could probably tell when I did this, but it's so simple that, you know, you can get by pretty fine without memorizing it, because it's such a simple thing. So the next thing they say, and then the other direction. So they show what the binary should be. They say this one is going to be 1. This one is going to be 3. This one is going to be 5. This one is going to be 7. This one is going to be 9. This one is going to be B. This one's going to be D. And this one's going to be F. So yeah, we got that correct as well. Next, and I would say as an aside, it is worthwhile to memorize hexadecimal and the binary and hexadecimal pairings. So that's probably something I should take a little bit of time to actually do, to be a little bit faster at that. It's not a big deal. Like I say, you can get by perfectly fine without having it memorized. But, you know, when it comes to things that would be useful to memorize, that's definitely one of them as a programmer. So that's something I should do as well, is I should just practice you know, memorizing the different pairings between hexadecimal and binary. That's a simple exercise you can do to make yourself a little bit better and a little bit faster as a programmer, because when you need to think about what's this hexadecimal number in binary, or what's this binary number in hexadecimal, well, if you have those memorized, it's literally instant to do that conversion. And that's one of those excuse me, that's one of those things you follow under the category of a simple trick that you don't need to do, but you know, it'll save you a little bit of time. Same like what I was talking about of how I want to practice writing machine code directly with RISC-V to get a feel for, what are some common patterns in terms of instructions, to just be able to eyeball some hexadecimal and say, oh, I see some instructions in this block of numbers, right? I see some stuff that looks like RISC-V instructions. That's something that you definitely don't need to do. But again, it's one of those things where it's like, if you just take some time to practice this thing, it'll maybe help a little bit. It'll maybe make you a little faster at something. Catch a bug faster or something like that. It's just a little thing that you can do. Same with this sort of thing. So I would recommend it if you want to, go ahead with that. I'd say that's a good thing to do, to memorize those patterns. RISC-V fields. RISC-V fields are given names to make them easier to discuss. And yeah, here they're introducing the actual names we were talking about. And they haven't introduced the concept that there are different instruction encodings depending on the kind of instruction, like if there are immediates or it's like a branching kind of instruction. And that's something we've covered, and I'm sure they will cover it as we go further in this chapter here, but they haven't covered that yet. They're just showing us the R type right now, and they say RISC-V fields are given names to make them easier to discuss, and this is what I already showed you just earlier today. Funct7 is the 7 bits at the top. Then you have RS2, which is 5 bits, RS1, which is 5 bits, Funct3, which is 3 bits, RD, which is 5 bits, and then the opcode at the bottom, the low bits, which is 7 bits. Then they say, here is the meaning of each name of the fields in the RISC-V instructions. And again, I already told you what the meanings are, but we'll go over it again. Opcode is the basic operation of the instruction, and this abbreviation is its traditional name. And then in the margin here, it has a definition of opcode as well. Opcode is the field that denotes the operation and format of an instruction. Next up, we have RD, which is the register destination operand. It gets the result of the operation. Funct3 is an additional opcode field. And they should have mentioned, in my opinion, that the reason it's called Funct3 is because, the 3 is because it's a 3-bit field, right? But yeah, it's just to help you distinguish the exact operation, the exact instruction that you're doing. Then you have RS1, which is the first register source operand, RS2, which is the second register source operand, and then Funct7, an additional opcode field. And they've drawn it out here, but it's exactly the drawing I already showed you that I did on Risky Business, although mine has all the different instruction encodings, whereas they just have the one here. And I guess they're going to go through the others next. One thing I should say also is I think some of it has changed. I think they maybe got rid of one type. Like I think there was like J-type encoding or something for branches. And I think they maybe don't have that as a thing anymore. I don't know. I haven't been following the changes in the spec. That's something that I should probably do, rather than just grabbing the latest spec and reading from it as I go through the Risky Business series, as we learn from the specifications and stuff. What I've been doing is I just grab the latest spec, whatever is up on the website, right, and read through it. I should probably actually like clone the repository that documentation is built from, and keep track of the commits that happen to it, right? Keep track of the change log would be a good idea. Because it is, a living standard. It is growing and evolving as RISC-V grows and evolves, because this is all very, new stuff. So yeah, I have JType listed here. Like I say, I'm not sure that's a thing anymore. I have a suspicion that one has been dropped, but don't quote me on that. So yeah, that's just something I need to maybe think of with my own series that I'm doing here. I should probably be keeping track of the changes to the spec because things do change. But yeah, let's keep reading here. A problem occurs when an instruction needs longer fields than those shown above. For example, the load register instruction must specify 2 registers and a constant. If the address were to use one of the 5-bit fields in the format above, the largest constant within the load register instruction would be limited to only 2 to the 5th minus 1, or 31. Yeah, so what they're talking about here is that if you only had this instruction encoding that they've shown us here, the R type, if you needed to do an immediate, you'd be pretty tight on space to do an immediate. So that's kind of the motivation for having these different instruction encoding types, is depending on the kind of thing you're doing with your instruction, you might need a different layout, right? Because, for example, in this instruction layout, this instruction encoding or format, we have these source RS1 and RS2, but they're only 5 bits long. So if instead of a register as one of the sources, if you want an immediate, so let's say you want to do an add again, but you don't want to put the operands you're adding into registers, you just know you're going to take some number and add 5 to it, for example. I just want to add 5 to a number for some reason, right? I just feel like adding 5 today. Okay, so we're going to add 5. Well, if you're going to add 5, you don't need to put 5 in a register, right? You can just pass that directly in the instruction, right? And if you look at this encoding here, you could actually do that if that's how it worked, which it isn't. But you know, a 5-bit number, you could have the RS2 be the number 5, right? Because it's just 5 bits. You can put whatever you want in those 5 bits, right? So rather than specifying a register, you could just put a 5 in there to say, you know, I want the immediate 5. Of course, that's not how it works because it expects that to be a register. So that would think you want the X5 register, for example. You know, it would think you want the 5th register, not the immediate 5. But the point is, with that problem aside, you also run into the bigger problem of, okay, I want, an immediate that isn't 5. I want it to be, 635, right? Or 632. Let's not do 5 again. 632, right? 632. Well, 632 does not fit in 5 bits, right? It's much larger than that. So you obviously can't stuff the immediate into this encoding because you only have 5 bits to work with. That would mean you can only add up to the number 31. You can add from 0 to 31, and that's obviously no good if you want to be adding immediates. So if you want to support something like that in your instruction encoding, not only would you need to have a way to say, this isn't supposed to be a register, it's supposed to be an immediate, you also need to be able to say, it needs to be a lot bigger. We need a lot more bits devoted to the source operand in that case. And we only have a fixed 32 bits to work with here, so clearly you need to totally redo this format, the instruction format, if you want to support something like that. And that's exactly what they do. They have different formats for different use cases. So that's pretty straightforward, right? It's we need it to be something like this, so we make the format be something like that. here's a problem, here's the solution. It's pretty straightforward, right? So this 5-bit field is too small to be useful. Hence, we have a conflict between the desire to keep all instructions the same length and the desire to have a single instruction format. This conflict leads us to the final hardware design principle. Design principle 3. Good design demands good compromises. That's a useful, have they been giving design principles? I don't remember design principles 1 and 2. But yeah, that's a good one. I like that. That's a nice rule of thumb, and that's something I stress a lot is, like with talking about the integers, for example, we talked a lot about how compromises need to be made. It's a physical machine. You have physical constraints. You have to make compromises, right? And so the job of the engineer is to choose good compromises to suit your use case the best. That's kind of what programming and engineering in general is all about. It's you have constraints, and within those constraints, you find the optimal solution for what it is you're trying to do. And doing that, you're necessarily needing to make compromises because you're not going to have a general solution that's perfect for everything. Right. And that's one thing in programming that you kind of see a lot of. People do these general purpose programs and having libraries that are meant to be very general purpose. And the downside of doing something like that is that you're sacrificing things. You're making compromises in other directions. The API might be too cumbersome because it's trying to support all these different use cases. You might have inefficiencies. It might be a lot slower than it could be because it's accounting for things that you might not necessarily, in your use case, you might not necessarily need that algorithm to do all this other stuff. But if you want the algorithm to be very general and support a lot of different use cases, you need to take that performance hit, for example, and that's an engineering trade-off, right? And generally in good engineering, when it comes to programming, I kind of think you shouldn't really be doing this overly general purpose programming. Maybe it's useful if you're doing something like scripting and you just want a really rich library that gives you a lot of stuff so you can write a program really fast and you don't care about the performance. That's a use case where you might want something like that. But in general, you want to think about, here's my use case, here's what I need to do to get done. What's the best way to do that, right? That's kind of what you want to have in mind when you're programming. And yeah, so I think this is a great rule of thumb, and I think a lot of programmers could use that lesson to keep that in mind when they're writing programs. Hey, I need to make compromises. I should be thinking about the compromises I'm making when I'm writing software in the first place, just being aware of the compromises you're making because you are making compromises. And then, when you're making those compromises, thinking about what are the best compromises, what's going to be good compromises to do a good job at what I'm trying to do, So I really enjoy that little rule of thumb they gave you there. That's a nice one. What were the design principles 1 and 2 though? I'm flipping through the book right now because I don't remember them doing a 1 and a 2. It's been too long, I guess, since I've been reading this. Oh, design principle 2, smaller is faster. Yeah, that's a good one. That's very true. That's good. Although that's not always true. That's kind of a okay. Yeah, they do say it's not guidelines such as smaller is faster are not absolutes. Yeah, I was just gonna say that too. That smaller is not always faster. For example, when you're optimizing code, oftentimes a longer sequence will be faster because you're doing something like loop on rolling or things like that where you're avoiding overhead, but the resulting code is actually longer. That's a very real thing that happens pretty commonly, actually. So it's not true that smaller is always faster, but it's a it's a nice little rule of thumb, and it's it's a good thing to keep in mind, especially as a programmer. Again, I think striving for a small, simple program, like when people write libraries, for example, single header C libraries are a great example of not necessarily going for speed, where they're saying in their little rule of thumb here, they're saying smaller is faster. Maybe that applies more in hardware than it does in software, I don't know, but keeping your library small is a great thing. And one of the things we see is people like to over-engineer these things and make these giant libraries that depend on a million other things, and they just build on top of stack and stack and stack up all these different layers of abstraction, and you end up with this huge bloated library that is just absolutely a monster. It's gigantic, and you are going to get terrible performance because you have this gigantic call stack, right? You're going through so many layers of abstraction before you get down to the the actual bits of stuff at the bottom that's doing the real work, that you end up with this bloated huge library that's not even good at what it does, because it's just over engineered to death, and it's just a a terrible thing. We see that all the time in programming today, and that's a perfect example of like bad engineering. You're making bad compromises. You're saving your own time as an engineer building on top of other people's work and relying on lots of dependencies, and you're avoiding actually thinking about the problem and doing the actual work to solve the problem. So you're making good compromises for yourself as an engineer, being lazy, right? Trying to not do real work. But and that can be good if you're like a startup. When you're at like a company, it's if you're at like a startup and they need to get a product out the door because they need to make money for the business to stay afloat, right? And if you have real world constraints like that, then that might be the right choice for you to make, because you're writing bad software, you're doing a bad job as a programmer. But the fact is, it might be a lot faster for you to do it that way, because you're not having to think about the real problems. You're not having to write the low level stuff. You're just gluing some stuff together really fast, and that can be useful in terms of maybe speed for yourself to write code. But you're not writing good code, you're not doing good engineering, and the result is going to be bad, right? But like I say, that's in some sense that can be the right decision, that can be the right trade-off for you to make in a kind of a corporate environment. And that's why I think that it's kind of a culture problem, that this is kind of the way the industry works. Software should not be developed this way, and the result is bad, and we see that all around us. But if you've worked in that kind of environment, if you've had a job where you're working at a startup or something like that, you kind of see it from the other side. You see that it's like, well, this programmer, the programmer there is not actually a bad programmer. They're just working under constraints where this is what they need to do to ship, right? And they need to ship, right? They don't have a choice. So it's kind of the culture that encourages bad software, in my opinion, that people need to ship, they need to get stuff out the door fast, because they need to make money, and that just results in bad software, in my opinion. Which is kind of why I do this handmade stuff, why I'm all about the handmade network and things like that. I like to just take my time and say, you know what, I'm just going to take however long it takes. I'm going to do as much research as I need. I'm going to study as much as I need. I'm going to do whatever it is I need to do so that I can do a quality job and make something that's actually really good. And so that might take a lot of time, but I don't have a deadline, right? I'm not trying to make money off this. I'm not trying to ship, get something out the door right away. I'm just trying to make really good quality software. And so the handmade approach can really be beneficial to that. The design principle 1 by the way, was simplicity favors regularity. And yeah, I mean, that kind of goes into what I was saying with the design principle too, as well, that, just, have simple things that are, they're simple, they're small, they do the job they need to do, and that goes into compromises as well of, you're necessarily going to be making compromises, but the compromises you should be making are the compromises for, doing a good job at what needs to be done. Here's the problem. What are the right compromises to get the best solution for that problem, right? The problem shouldn't be, you shouldn't have a culture, ideally, in an ideal world. You don't want to be in a culture where the problem you need to solve is, I need to get this software done to, yesterday, right? The software needs to be done yesterday. That's not the situation you want to be in as a programmer, right? That's what they would always say at my previous job is, we need this yesterday, right? And yeah, that's just, when you're working in that environment, you really do see the other side of it of like, this is why bad software gets made, right? Because this is the culture. And it's like, you can't blame the company because, they're just trying to stay afloat. They're just trying to make money, it's a, it's a startup situation. That's just how it is, right? That's the economics of it. But yeah, it's just interesting to see that it's like, okay, well, that's why we're in this situation. That's okay. It kind of makes sense, right? This is why software is so terrible. But yeah, but you can definitely make money doing quality software too. Look at Alan Webster with 4Coder and everything. He was like studying in college, and I guess it was RAD Game Tools that picked him up. He was able to just, quit college and go work for them. So he's got a great job doing great stuff at a great company. And he's able to work on his, 4Coder project and do, really good quality work. I don't know what the culture is exactly at RAD, but the point is, I'm pretty sure it was because of 4Coder that he was able to do that he was, on the radar of the people at RAD Game Tools, and they were like, that guy is someone we want to work for us, right? Like, 4Coder is an amazing piece of software. This guy is a really smart guy. He's someone that we should pick up and, actually work with. I don't know Alan personally, and I don't know, the situation at RAD Game Tools at all, but I know everyone who works there is very, amazing, talented people, and they do amazing work. And I know, what Alan has done with 4Coder, and it's, it just all kind of fits together there, that story. So, and that's, a direct result of like, someone doing quality work like what we're talking about here in handmade-network type stuff, this handmade software, that resulted, I think, and again, I'm just assuming here, but I believe that directly resulted in, Alan being able to get an amazing job at an amazing company, right? So there are, economic benefits to doing this type of thing. It's not like this is, totally economically, infeasible. And 4Coder is a commercial product. It's not like, he's doing it for free. He's making money off 4Coder. So, this is very much a viable type of thing. But anyway, sorry for kind of digressing there, but yeah, some interesting things to think about when it comes to these sorts of rules of thumb of, good design principles. It kind of leads you down that road of thinking like, how does this apply to handmade software versus the kind of, enterprise software we see around us today? And, are they following the design principles that they're talking about in this book? Or, is handmade more in the realm of good design principles? It's interesting to ask those questions. It's always good to, ask questions and see how it applies to the real world. And of course, even the book mentions that these principles are not set in stone. There are plenty of things that, go against the grain of this sort of thing. But, you never want to take a rule of thumb as absolute. That's why it's a rule of thumb, right? But anyway, Sorry for kind of going on a long digression there, but let's continue reading this here. Let me just check. Okay. How many pages do we have? Ideally, I'd like to get through the entire 2.5, but I don't know if we're going to be able to get through the whole thing today. Let's just keep reading and see how far we get before I decide to call it quits. So, the compromise chosen by the RISC-V designers is to keep all instructions the same length, and again, this is an oversimplification, thereby requiring distinct instruction formats for different kinds of instructions. For example, the format above is called R-type for register, and again, that's what I had already mentioned, that's the R-type. A second type of instruction format is I-type, and it is used for arithmetic operands with one constant operand, including add I and by load instructions. I think that was maybe a typo in the book, and by load instructions. I think they mean and load instructions or something like that. The fields of the I-type format are, and here, let me, since we're going to be going over these different formats, let me mouse over to that instruction format stuff. Where was that? There it is. Okay, so yeah, you see the I-type is this one right here. And so it has 12 bits immediate, 5 bits RS1, 3 bits funct3, 5 bits RD, and then 7 bits of opcode. So you see that this has 12 bits of immediate, whereas the R-type only had 5 bits for their source operands. And so obviously 5 bits wasn't good for fitting an immediate in there. 12 bits is, you know, much better, not perfect, but you know, you have a much more useful range with 12 bits than you do with 5 bits. 5 bits are really useful for the register type encoding because 5 bits lets you hold 32 different values, right? And there are 32 registers. So for a register type encoding, is an obvious choice where each integer just directly corresponds to one of the registers. Whereas with the immediate type, you want something bigger. You want to be able to hold more than 32, you know, more than 0 to 31. That's not really good if you want to have an immediate, like I said, you want to add 632 to some number, right? If you want to do that, you know, it's much nicer if you have 12 bits of immediate so that you can fit that, you can actually fit that number in there, right? That's the deal here. The 12-bit immediate is interpreted as a 2's complement value, so it can represent integers from -2 to the 11th to 2 to the 11th minus 1. When the I-type format is used for load instructions, the immediate represents a byte offset. So the load double word instruction can refer to any double word within a region of plus or minus 2 to the 11th, or 2048 bytes. It says plus or minus 2 to the 8th, or 256 double words of the base address in the base register RD. We see that more than 32 registers would be difficult in this format, as the RD and RS1 fields would each need another bit, making it harder to fit everything in one word. Let's look at the load register instruction from page 71. What was 71? So that was when we were doing 2.3 operands of the computer hardware. And I guess at that point they introduced the load instruction. It says they have an example on this page compiling using load and store. So you could easily look that up in Sonera if you need a refresher. It was 2.3 compiling using load and store as the example that they went over there. Let's see here. So where were we? Yeah, so let's look at the load register instruction from page 71. It was load x9 64 x22. So that's loading. They have an address in x22 and then an offset of 64, and they're loading that into x9. And then the comment is temporary register x9 gets a indexed by 8. And again, it's by 8 because they were working with double words. So the 64 is representing the eighth index. Here, 22 for x22 is placed in the RS1 field, 64 is placed in the immediate field, and 9 for x9 is placed in the RD field. We also need a format for the store double word instruction, SD, which needs 2 source registers for the base address and the store data, and an immediate for the address offset. The fields of the S-type format are immediate bits 5 to 11, which goes in the 7 bits. And then the 5 bits after that is RS2, and then you have RS1 and Func3, just like usual. But then you have the 0 to 4 bits of the immediate in the 5 bits after Func3, and then the opcode as the last 7 bits. It says the 12-bit immediate in the S-type format is split into 2 fields, which supply the lower 5 bits and the upper 7 bits. The RISC-V architects chose this design because it keeps the RS1 and RS2 fields in the same place in all instruction formats. And again, if you look at my drawing there, you'll see that that is the case, that the RS1 and the RS2 are all in the same place in all the different instruction formats. You'll see the same is true for the ones that use an RD. The same is true about the opcode. The same is true about anything that uses a Func3. So they kept it all very uniform, which actually has benefits for the hardware design, I believe. And I believe that was discussed some in the RISC-V reader. So if you watch some of those episodes, we only did like 3 episodes of that so far, and it's kind of been on the back burner, but I believe they discussed this in that book as well. So you can get some more background on the design decisions there. And also, if you just read the spec, if you actually literally just go to the spec, which we do on Risky Business, they do a very good job in the spec of detailing their design decisions in comments within the spec. It's a very good read, so I'd recommend that as well if you want to know more about that sort of thing. The different kind of compromises or trade-offs that they make doing the engineering of making the ISA, right? There are real trade-offs that need to be made there, and they make them. So let's keep reading here. Keeping the instruction formats as similar as possible reduces hardware complexity. Yeah, that's what I thought. Similarly, the opcode and Func3 fields are the same size in all locations, and they are always in the same place. In case you were wondering, the formats are distinguished by the values in the opcode field. Each format is assigned a distinct set of opcode values in the first field, which is the opcode field, so that the hardware knows how to treat the rest of the instruction. Figure 2.5 shows the numbers used in each field for the RISC-V instructions. So they show, they have a table here. They have an add instruction, which is format R, and then Func7 is just 0. RS2 is a register, RS1 is a register, Func3 is 0, RD is a register, and then the opcode is 0110011. Okay. So in terms of an add, The only thing that's really, distinguishing it is just the opcode is 0110011. But then if we have a sub, which is also R-type format, sub is the subtract, the funct7 is 01000000. So rather than being all zeros, there's a 1 there in one of those bits in funct7. So that's how it distinguishes between add and subtract, right? Is one of the bits is different in funct7. But other than that, it's all the same. So rs2 is a register, rs1 is a register, funct3 is 0, rd is a register, and then opcode is 0110011. So the opcode is the same for add and subtract, but funct7 distinguishes between the two, okay? And then we have a table following that one, which is some more instructions comparing them. We have the add immediate instruction and the load double word instruction, both of which are format I for immediate, right? And then instead of having a funct7 and an rs2, these take an immediate, right? And so in the case of add immediate, it just takes a constant. And in the case of load double word, it takes an address. And then for rs1, both of them take a register. Funct3, for add I, it's 0, just like it was for add and sub that we saw earlier. And then RD is a register for that as well. But then the opcode is different. So again, we're talking about how the opcode distinguishes between R-type, I-type, S-type, and so on and so forth, right? So the opcode, again, for add and subtract, which were register type format, it's 0110011. That's what the opcode is. But for the I-type here, this add immediate instruction, it's going to be 0010011, right? So that's a different number, right? That's a different opcode. So that's how it distinguishes that add I is different. But then the load double word actually has a different opcode as well. So it's an I type as well. The immediate is an address. rs1 is a register. Funct3 is different. It's 011. And then the RD is a register again. But then the opcode is 0000011. So different opcode for the load double word instruction. And so that's another thing to point out is that the formats, it's not that the opcode just indicates the format. It kind of indicates ranges of different things. And this is clearer if you look at the, like they have in the spec or in the book, I think in the, in this green card that they include in this book, and the RISC-V reader has a really nice table in it as well. You can see opcodes listed for the different instructions for like the base ISA. And so yeah, it literally just has a table on the card here where you can see the different opcodes and what falls under them. And that's a pretty useful thing to look at if you want to get a feel for how the opcode is being used to organize the different instructions. I'd say that's the best way to really learn that, to really understand that, or get a feel for that, is to look at a table of all the different opcodes for the different instructions. And I guess I'm not going to show you that here because I don't want to write it all out. And I'm not going to take the time here to open up the RISC-V spec to find it there. But yeah, it's that's worth looking up and taking a look at if you want to get a better feel for how these encodings are working. Because I think this example that they're giving here doesn't really make it clear. they're saying how it uses the opcode to distinguish between the different fields, but then they're also showing you that it's not quite as simple as that. It's not like one opcode corresponds to one field. That's not exactly how this works, right? So yeah, I recommend looking at a table of the opcodes, which you can find in the spec or in the RISC-V reader or in the green card included with this book. They finally here they have a different example. The store double word instruction, which is the S format. It has, instead of a 12-bit immediate here, where you would have funct7, they have an immediate, so a 7-bit immediate for an address. And then you have RS2, which is a register, RS1, which is a register. Funct3 is going to be 011, same as it was for low double word. And then there's an immediate, instead of RD, there's an immediate. So the 7-bit immediate and then the bits for where RD would be are, combined together to make one big immediate there. And then the opcode is 01000011, which again is different than the previous opcodes we've seen. Figure 2.5, RISC-V instruction encoding. In the table above, reg means a register number between 0 and 31, and address means a 12-bit address or constant. The funct3 and funct7 fields act as additional opcode fields. So yeah, that's how that works in a nutshell. Not a very satisfying explanation in my opinion, because it's kind of crazy how the RISC-V instruction encoding works, because they're really trying to be clever and pack a lot of stuff into the 32 bits that they're working with, while also being nice for hardware designers, being something that's good to implement in hardware. There's a lot of considerations that went into all this stuff. So it's not that simple. It's kind of a confusing format. I mean, it's easy enough to follow if you look at the tables of look up the different types, encoding types, and look at a table of all the opcodes for stuff. It's not that bad really, but there's not like an easy explanation for for how it works exactly in terms of like the opcodes, because yeah, like I say, it's kind of all over the place with the funct7 and the funct3 and the opcode, and it doesn't correspond exactly with the the R type, the I type, so on and so forth. So in that sense, it's hard to give a very satisfying explanation of that very briefly. So I think that's a bit of a failing of the book, I would say. I'm not pleased with their covering of this topic, but that's really just because it's not that clean, honestly. That's just how it is. That's just the reality of the encoding, because they needed to make real world engineering decisions. They needed to make trade-offs, and like the book said, you need to make compromises and stuff like that. That sort of thing all went into this instruction encoding. So yeah. Anyway, they have an example here, translating RISC-V assembly language into machine language. We can now take an example all the way from what the programmer writes to what the computer executes. If x10 has the base of the array A and x21 corresponds to H, the assignment statement A indexed by 30 equals H plus A indexed by 30 plus 1. So they want to actually take it all the way to machine code. So let's work this example. Okay, so A30 equals H plus A30 plus 1, okay? So this is like C code, right? This is the statement we're going to compile by hand, right? And so the first thing we need to do is assemble it, right? We need to convert it to, or I shouldn't say assemble it, we need to convert it from C to assembly, right? So we're going to lower this from C down to assembly. And they show that in the book because this is an example, right? So they give you the answers in the book right along with it, but we're gonna try to do it without looking at that first. So as I do, that's generally what I do as we go through this is I work through the examples rather than just reading the answers. So it said x10 has the base of the array A, so I'm just going to put over here a note that A is x10. And then it says x21 is H. So H equals x21. And yeah, now they want us to convert this all the way down to machine code. So let's see what we have here. Well, first of all, is that a, okay, yeah, that's a +1. So we have H, which is x21, plus A indexed by 30 plus 1. So first of all, A indexed by 30, we're going to need to load that into a register. Now, they're probably not going to use the proper calling conventions, as I've noticed in the past in the book, but we're going to try to use the proper calling conventions. So let me see here. H is in x21, which would be a saved register. And then we have A is in x10, which would be a function argument or return value. Yeah, we're gonna load A indexed by 30 into a register. So I'm just gonna put it into a temporary register because that is a temporary. So where's our first temporary register in the calling convention? That would be T0, which is x5. So we're going to do a load double word because their examples are all working on double words. So we're going to do a load double word. Now, what's the syntax for the load? They don't really make that clear on the green card. That's one thing I don't really like about the green card, but the RISC-V reader would be my go-to for seeing examples of instructions. So I'm gonna pop open the RISC-V reader. Or I would if I if I had it setting here. Where did I put the RISC-V reader? Just a second. Aha, I've spotted it. I have it under boxes of the things we've been opening. That's why I didn't see it. It's buried under boxes of things we have been opening. All right. Okay, so for a load instruction, what I'm going to do is I'm just going to head over to the back of the book here. And they have them sorted alphabetically. So here's load double word. And the way you write it is LD, and then the register destination, and then the offset, and then the RS1 in parentheses. So we're going to load. The destination register I said is going to be X5 because it's a temporary. And in practice, if I was programming in assembly, I would actually write this. I would actually write like T0 instead of X5 because it refers to the same exact register, and that's the calling convention. And that just makes it clear that it's a temporary, right? T0, that's the first temporary. So I'm going to be loading into X5. The offset is going to be 30 times 8 because it's double words, right? So that would be like what, 240? So I believe this would be 240. And we could write that in hex. I don't know if they want it to be written in hex or not. I'm just going to write it in decimal. And then A is going to be X10. And yeah, that should be good for the load. Next thing we need to do is H plus A30 plus 1. So, and again, I don't know if we're allowed to destroy H or not, but you know, let's just put it into I could destructively use X5, so I could do H plus A indexed by 30. I could put that into X5 because we have one of the arguments in X5 and we're not going to be using that again after that. So I could just reuse X5, which I think I'm going to do. I'm going to guess that they put it into another temporary. So I'm just going to take a guess here that they actually use multiple temporary registers, but I'm not going to do that. I'm just going to reuse a register. So I'm going to say add, we're storing into X5. What we're adding is going to be X21, which is H, and then we're adding the A indexed by 30, which is what we loaded into X5, right? Next up, we're going to need to add 1 to that. So I'm going to do add X5, X5, 1, right? So that'll just add 1 to it. After that, we're going to need to store double word. So that'd be an SD instruction. And looking in the RISC-V reader, like I say, it's alphabetic, so here we go. Here's SD. You do RS2, SD, RS2, comma, offset, RS1. So RS1 plus the offset is going to equal RS2, basically. So yeah, we're gonna say we want to store x5 because that's the result of our addition, right? So store x5, and we're going to store that into A30 here. So A is x10, right? So and then the offset is going to be the 240 again. So it's like that, right? And that should be good in terms of translating these instructions into assembly. The next thing we need to do is actually translate these into machine code. So let me see here. So I'm going to write it to the right, and I'm going to write it in hexadecimal. So let me see here. First up, I'm going to use the RISC-V reader since I have it right here. I'm going to page through it until I find that table. Here it is. All right, so first up we have a load double word. Is it LD a pseudo instruction? Let me page back here. Oh, it's RV64I, right. This is a table of 32. Let me jump over to the chapter for RV64. I don't know if they have a table for RV64. Let's see here. Where is that stuff? Oh, yep, they do. Okay, LD. All right. Okay, so the bottom 7 bits are going to be 0, 0, 0, 0, 0, 1, 1. So I want to write this in hex. It's going to be a little bit awkward because we're working right to left. How do we want to do this? Well, one thing we should do is I guess we should convert the 240 into hex because we're going to need to have that in either hex or in binary for the, actually writing out the machine code, right? So let me see here. I'm going to go into mouse mode. All right, now. So 240 to hex. So that's F0. All right, so let's start by just organizing, like doing what they did. I think the best way to do it is kind of what they showed, where doing it in decimal, actually. So like we're gonna have immediate yeah, so the immediate goes in the first field. So that's just going to be 0xF0. And then the next field of the load is going to be the RS1, which is going to be the X10. So that's going to be 10. And then we're going to have the 0, 1, 1 comes next in this encoding. Next up, we're going to have the destination register, which is our wait. Yeah, that's right, because we're doing the load. So 5. I should make this clear because, you know, I'm mixing hexadecimal, binary, and yeah, I'm mixing hexadecimal, binary, and decimal as I'm writing this out here. Sorry about that. So yeah, the destination is going to be 5 for the X5 register. And then we're going to have 1, 1 as the opcode. So I'm just going to write that as 1, 1B. Right, and then we'll take another pass and actually write these out in binary properly. But for now, I'm just kind of getting the feel here of putting these things where they should be, if that makes sense. So let's flip back to the add, or the table for the 32-bit stuff. Okay, so in the add, oh, and this can be in an add I, can't it? Or I guess technically it is an add I, and I wrote it as add, which I believe you can do this in, it'll do it as like a pseudo instruction and actually turn it into an add I, but this is an add I, right? Because we're adding an immediate one, right? That should be noted. Okay, but first thing we're going to do is a normal add between 2 registers. Okay, so that one is going to be the number 0 in the first field. In the next field, it's going to be RS2, and then we're going to have RS1. So that's going to be 21, 5, and then we're going to have 0 again, and then the destination, which is 5, that 5. And then what comes next? 0, 1, 1, 0, 0, 1, 1. All right. Next up, we're doing the add immediate. So that one, let me find that here. So first thing we put is the immediate. So that's just going to be 1 is our immediate. So I didn't really fit this on the lines perfectly, so I'm going to skip a line and put that down here to keep it lined up better. So we put the immediate first, which is the 1. Then we put RS1. So that's going to be X5. So that's just going to be a 5. Next up, we put a 0 and then the destination. So there's the 0. The destination is going to be X5. So we put a 5. And then it's going to be 0, 0, 1, 0, 0, 1, 1. And that's going to be in binary. All right, and finally, we need the store destination, the store double word. And again, I'm going to need to flip back to the 64-bit stuff. Where was that? atomics, vector extensions. I may be too far, aren't I? Floating points. Multiply and divide. Oh, here we go. RB64. Okay, so this time we're doing a store double word. Okay, so this one splits up the immediate, but our immediate is 0xf0. So let me think here. So if our immediate is f0, that's 8 bits. It's a byte, right? And we have 0 to 4, so 5 bits of that goes in, 5 bits of it goes in where the RD would go in other formats, and the rest of it goes in the top. So if we're going to split that up, so there's the F, and then here's the 0. So if we're going to split the 5, we're going to split it here basically. So we're going to have this number, which is 7. So we're going to put a 7 here. And then we're going to put RS2. And let's see, I need to remember the encoding here. RS2 is the destination for a store, right? Let me double check that. Or that's the source. RS2 is the source. RS1 is the destination. So okay, so the source is going to be x5, so we put the 5 here. And then we put the destination next in RS1, so that's going to be 10 for x10. And then after that, we put 0, 1, 1. Let me make it clear again that, you know, these are decimal. Okay, and then let's see here. After the 0, 1, 1, we put the low 5 bits of the immediate. So that's going to be well, that's just going to be 0x 10, right? And then 0, 1, 0, 0, 0, 1, 1. And yeah, I believe that's everything. And I think that should be good. So let's take what we've just translated here and write it out a little bit cleaner as here. I'm going to turn my mouse on for working with Milton. I still prefer mouse for moving around in Milton, I think. Okay, so we're going to take these notes and translate them into something a little bit more useful. So first of all, we need to note how many bits each of these fields are, right? Because I just wrote out the values for the fields, but I didn't write out how many bits for each. So I believe this should be 7, 5, 3, 5, 7, right? Is that right? That would only be 27 bits. That can't be right. Okay, let me take a look at our encoding here. I think I missed something when I did this. This one here. So let's see here. Let me open up the RISC-V reader once again to double check my work, because clearly we missed something. Okay, RV64, we're doing a load. So we have the immediate, then we have RS1, then the 0, 1, 1. So immediate, RS1, 0, 1, 1. Then we have the destination register. Okay, and then the bottom 7-bit opcode. It's a 12-bit immediate is the thing. So this is 12 bits. Now does that add up? So 10, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Yeah. Okay. So so if we have 12 bits here, that's going to be 0x0, right? This is 4 bits. And then to get to 12, we put the F0. And then we have 5 bits. Yeah, we're going to need to work right to left because it doesn't split evenly like we talked about. So I don't think I'm going to be able to I think I'm going to need to work right to left. So let's do that. We start with the 7 bits here. So if we so this is going to be like 3, right? And then 0, and I'm working bottom to top here, right? So well, actually, I need to start with the 5 here. I need to see what that is. So 5 in decimal to binary is going to be, you know, 0, 1, 0, 1. And then like this 1, 1 BB is going to be 0, 0, 1, 1, but this is 7 bits, right? So it actually needs like 3 more bits of padding. So you'd put like 3 zeros in here, and then you'd have the 1 next, right? Because that'll give you the 7 bits, and then the next bit starts the next one. So this is actually going to be an 8, 1, 0, 0, 0. So this 3 corresponds to this, but then this isn't going to be a 0. This is actually going to be an 8. Right, and then so we've got this much. Now we have 5 bits here for the what is this, destination register. So here we have 3 bits. We can round this out to a nibble with 1 extra bit of padding, but then we're going to need to start bleeding into the next number, which is the 0, 1, 1. So it's going to split right here, right? So what you're going to get is a 2, a hexadecimal 2, or wait, I think I'm thinking about this wrong. Okay, so what you have is the 0, 0, 1, 1, but then you have 3 for padding, and then the 1, and then you have 0, 0, 1, 0, and then you have the 1, 1, 0, and what comes next? Decimal 10. So we can put a 0 here for padding, right? Let me see, this is 3 bits. So it's not actually padding, it's part of the next number here. But the 0 works because it's a 10, right? Which is 8, 9, 10, right? So you have a 1 here, and then you have 2 zeros and a 1 here. Okay, and then okay, after that we have the 12 bits of the immediate. So you have 1, 2, 3, 4, and then you have 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, so this is what I get. So if we split this up into groups of 4, this is what we get. So we get 0x 0, F0, and then this 1001 is going to be 9, and then we have 3, and then we have 2, 8, 3. So that's the hexadecimal of the instruction that I got, if I did everything right. And let me just write out the binary to, I guess, here, let me, I'm gonna redo this because I want to write the binary first, because that's what I ended up needing to do anyway. Since it doesn't split nicely, you kind of need to start with the binary. So this goes 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. And I don't know in the example if they give the hex as well, or if they just give the binary, but I'm going to do the hex regardless because I want to. Just for my own sake, because like I said, I want to do hand hand coding in machine codes, and if I'm going to do that, I want to get familiar with what instructions look like in hex, and so this is a good first exercise for that. Okay, so there's the binary, and then that is just going to be 0, F, 0, 9, 3, 2, 8, 3. All right, there's one instruction. Okay, let's keep going here. So next up, we have an add. So let me see if I can guess the encoding here. I believe it's 7, 5, 5, 3, 5, 7. So that's 10, 20, 25, plus 7, 32. Yeah. Okay, so we're going to have 7 bits, 0. So 1, 2, 3, 4, 5, 6, 7. Next up, we have number 21. So we're going to need to convert that to binary. So 21 equals, and that's in decimal. So let me see here. So 16, 17, or wait, 16, 17, 18, 19, 20, and then 21. So we're working with 5 bits here. It's going to be 1, 0, 0, or wait. Oh, yeah. I just, I had my fingers wrong. It's, so yeah, it's going to be this finger, this finger, right? So 1 0 1 0 1. So 1 0 1 0 1. Okay, next up we have a 5, 5 bits again. So, of course, a 5 is just 0 1 0 1. So there's going to be a leading 0. And then 0 1 0. And then there's going to be a 1 over here. Okay, next up we have 3 bits that are going to be 0. And then we have another 5-bit 5. So that's going to be 0 0 1 0 1. And finally 7 bits that are going to be 0 1 1. Or sorry, okay, where am I? 0 1. Okay, yeah, we do want the 1 there. And then 0 0 1 1. Okay, this is going to be 0 1. What do we have there? Looks like that's supposed to be a 0 1 0 1. So that's a 5. And then we have a 2. And an 8. And another 2. And then 11, so that's going to be a B. And then a 3. All right. So when we're looking at it in hex, the most useful thing I think to eyeball is the opcode, in that it's 7 bits. So it's not super clean, but you know, if you look at the low byte, basically, like the first nibble corresponds directly to the bits, and then the second nibble, if the high bit is set, you ignore that. So like an 8 is going to be minus the high bit, so that's just like a 0. And then like the B, again, you need to minus the high bit. But yeah, looking at the hex is actually not very useful in for eyeballing in RISC-V, because of the way it doesn't split evenly. You can't really eyeball hex and make out instructions, I think, because of how it splits like this. It ends up kind of nasty in hex. So if you're writing machine code, I think you really don't care so much about the hex. You care more about the binary And then, if you're going to type it out, I guess for convenience, you could get used to writing it in nibbles like I'm doing here, and then actually type it into your editor in hex. But I feel like for viewing it, you actually want to see it in groups of 32 bits in binary. That's the most useful. Maybe visualize it not so much in hex, but visualize it based on the encoding of the fields, basically. I think that's kind of what you want to do. So you don't actually want a hex editor so much. You actually want to, if you want to do this by hand, machine code by hand, you don't really want a hex editor. What you want is something that views memory split into the different the different sizes of the encoding types, more or less. Something that splits it more like this. And because it varies between encoding types, you'd maybe want to see it be able to toggle between the different views, the different instruction type views. I mean, it's kind of hard because the nice thing about hex is you don't need it to be, with a more traditional instruction stream, is you don't need it to be aligned. You can just kind of eyeball it. You can just eyeball the hex and pick out instructions, right? Where it's like, this is a common sequence that looks like it's instructions, so you can kind of guess where the instructions are aligned to, and kind of figure out what you're looking at just by eyeballing it. But to do that in a RISC-V program is a little bit trickier, because you can't really eyeball the hex. And then if you want to look at it with like a custom viewer that's splitting memory up based on the encoding types, it varies. The encoding types vary between instructions. So if you're looking at a stream of instructions and trying to pick out where the instructions are aligned to, it's going to be difficult, because they're potentially in different encoding formats, and that just makes it more difficult, because the visualization isn't going to be able to show that very cleanly. So I think this is kind of an open problem for me, of how do you best visualize if you just want to open up like an executable file and scroll through it, and you want to be able to pick out with your eye, just kind of eyeball it and figure out where you think the instructions are, where you think some instructions might be. Like, these look like common instruction sequences. That's actually kind of difficult. That's harder than it would be in other ISAs, where it's more cleanly split into hex. Like, this is not nice in hex. This is actually kind of difficult. So that's an interesting realization for the day. That's useful to be aware of. I'm not sure how I'm going to solve that problem, because I really want some kind of tool where you can do this, and it feels like maybe the best thing is to not actually have something that doesn't like a hex editor doesn't understand what it's looking at. It's just dumping raw memory as hexadecimal. But I feel like if you want to play around with RISC-V machine code, what you actually want to do is have something that parses different file types, like an ELF file, right, which is what the file format would be on Linux. To be able to parse that and understand that, so it understands where instructions are in the instruction stream, and then it can actually parse that and display it to you in a nice format, because it understands what it's looking at, right? I feel like you need a program that understands what it's looking at, really, if you're going to mess with this sort of thing. Because if it doesn't understand what it's looking at, and you're trying to get it to show you RISC-V instructions, it's going to need to do some guesswork to figure out where the instructions are, and that's going to be pretty hairy, because you definitely can't do it by eye. So the program would have to do it for you, and that would be kind of a hairy algorithm. to have it try to guess where the instructions are, and then display the what it thinks the instruction stream is. I think it's the cleaner solution is to have a program that actually understands the format of the file you're looking at. So that's an interesting point. And for writing it by hand too, when you're writing an instruction, if you're directly coding in machine code, what you'd probably want is, instead of something that just lets you input hex, that just a hex editor, if you have something that understands what it's looking at, you'd probably want to input something more like what I was writing out in here, like to be able to input, maybe you want to input hex, maybe you want to input decimal, maybe you want to input binary, depending on what you're doing, depending on what field you're working with. It might depend what you want to input, but regardless of how you do the inputs, you structure the input thing, it would go by field, right? It would let you edit fields rather than just editing hex, raw, split the file up by nibbles. You split the instruction stream by field, and then it lets you directly edit each field and type in a number in hex, or maybe you can type in multiple bases, but something like that is really kind of what you want. You don't really care so much about the hex. That's an interesting realization of the day, because of how it it doesn't split cleanly. So yeah, that's good to know. Let's continue here. So I think I got this one. Now the next one, the other thing is it's going to be kind of difficult to compare our answers to the book too, because we're using X5, for example, and I don't know what registers the book is going to pick, and so it's not going to be super easy to compare our answer with the book, but we're gonna figure it out. So anyway, next instruction is add immediate, right? This one down here, and that instruction, let's see here. So it takes an immediate. So this is the 7 bits here. This is 5 bits for a register. This one's 5 bits for a register. So this is going to be a 12-bit immediate, and this is going to be func3, which is 3 bits, right? Yeah, I'm pretty sure. So let's start writing this out. So for the 12-bit immediate, we're going to do right. That gives you the number 1 in the 12-bit immediate. Next up, we have 5 bits, and we're putting 5 in the register. So that's going to be 0, 0, 1, 0, and then the next nibble gets the least significant bit there. Okay, and then we have 3 bits that are all 0, and then we're going to do a 5 again. So 0, 0, 1, 0, 1 in the next bit, and then we finish it off with the 7-bit opcode. So 0, 0, 1, and then finally 0, 0, 1, 1. And just for the fun of it, we'll continue putting these in hex. Not that I think it's really useful, but we're going to do it just for the heck of it. So 0, 0, 1, 2, 0, 0, 1, 2, 8, 2, and then 9, 3. All right. And the final instruction is this store double word. And let's see here. So it looks like we have 7-bit immediate, 5-bit, 5-bit register, and then another one, and then the 3-bit opcode, and then 5-bit for another register, and then 7-bit the destination. So writing that out, the 7 is going to be, let's see, this is a 7-bit immediate. So we're going to do 3 bits, which are the leading zeros. And then for the 7, there's going to be something like that. And then we have the 5-bit register. So that's going to be 0 here, and then 0, 1, 0, 1. Okay, and then the next one is another 5 bits. So I'm going to do a leading 0. Well, assuming it's a leading 0, it might not be. Yeah, it looks like it's actually a leading 1, because the number is 10. And I believe that's 10 decimal, right? So this would be a 1. And then we're going to have 0, 0, 1, 0, right? And then 0, 1, 1. And now we have a, it looks like that's a hexadecimal 10 this time. So that's going to be 0, 0, 0, 1, 0, 0, 0, 0. I think I got off somewhere, right? Because oh, that's supposed to be 5 bits. That's why. So 0x10 can't be right. I think that was a typo. I probably meant 0xa, I'm guessing. Let me take a look at what the instruction we're encoding is. Okay, so we're doing a store. We have offset right here. But wait, why did I put 0x7? If that's the offset? Shouldn't the offset be 240? Or F0 in hex? Right, the 5 makes sense. The 10 being the destination, I believe. Okay, I'm gonna need to look back at the encoding for SD. Oh, okay, I see. I guessed wrong. That's the problem. It's or well, I mean, I split it right, but the reason it's the immediate is like it is because it's a 7-bit immediate for the high bits, but then the low bits are the 5 that comes before the or comes after the opcode, right? So that's why there's a 0x7 and a 0x10, right? Because that's the 0xF0 split as I drew over here, right? This is a 7, the top 3 bits, and then the low 5 bits give you a 1 and a 0, right? So yeah, that's kind of confusing. I wrote it as 0x10 because that's what it is in hex, but it's actually a 5-bit immediate. So the 1 there is actually just indicating a single bit, right? A little bit confusing there, but I've got it now. I understand. So this is a 1, and then there's 3 zeros to finish off that nibble, and then finally another 0 there, and now we have the 1 0 0, and then I believe this is supposed to be 0 0 and 1 1. Or wait, no. Let me redo. Okay, so what we have here is we need to end off the 5 bits here. So we have a leading 0, but then we have a leading 0 here, and then a 1, and then 3 zeros, and then 1 1. Yeah. Okay. Now, putting that in hex, we have 0, E, right? And then 5, 9, 3, 8, 2, 3. So this is the entire bit stream laid out for you. This is our compiled code. So this was the line of code we started with. A indexed by 30 equals h plus a indexed by 30 plus 1. And that we translated to the following machine code. And here you can see it in hex as well, which is not super useful, but there it is anyway. So let's get back to the book and see what they said. And again, our answer is probably going to be different than what's in the book because it's the book is probably going to allocate registers a little bit differently than we did. It tends to be hard to predict what registers they use because they don't exactly follow the calling conventions all the time, I noticed. So we'll see what they do. All right, so first of all, they compile it down to assembly. So let's compare our assembly code. So they do LD X9 240 X10. So they decided to use the X9 temporary instead of X5. Let me just check the calling conventions. And again, I feel like what happened is the book was written before, like with older calling conventions. I'm guessing the calling conventions changed since the book was written, but the green card is up to date. So I don't know. But they used X9, which is a saved register. It's saved register 1 under the calling convention. So, you know, clearly that's wrong because we're definitely using a temporary here. It's definitely a temporary. So, yeah, they didn't follow the correct calling conventions. And again, my theory is that they probably were following the correct calling conventions when they wrote it, but I'm guessing that the calling conventions changed at some point. And so the book is actually out of date in that regard. That's my guess, but don't quote me on that. So they did LD X9 240 X10, which again is the same thing we're doing. We just chose a different register. Then they do add X9, X21, X9. And again, we do the exact same thing, again, just with the X5 instead of X9. And so they actually did choose to destructively use the temporary like I did. So they are overwriting their temporary register, X9 for them, X5 for us. They did it the same way that we did. Literally, the only difference is that we just chose a different register. So then they do add I X9, X91, which is equivalent to our add I X5, X51. And then finally, they do SD X9 240 X10, which is exactly what we have there, just with the X5 again. So now, what is the RISC-V machine language code for these 3 instructions? So for convenience, let's first represent the machine language instructions using decimal numbers. From figure 2.5, we can determine the 3 machine language instructions. So this is the first thing I did when I was translating it as well. Except I didn't use decimal. I used a mix of hexadecimal and decimal and binary. So my notes are a little bit ugly, but so they say first you have the immediate let's see, did I read this top part for convenience? Let's first represent the machine language instructions using decimal numbers. From figure 2.5, we can determine the 3 machine language instructions. And here they have them drawn out. So the immediate is 240 in the first instruction, which is our F0. And then RS1 is 10, that's what we have. Funct3 is 3, that's what I wrote as 011. Funct RD is 9, which is 5 for us because we chose a different register. And then the opcode is 3. Then for the next instruction, funct7 is 0, that's what we wrote. RS2 is 9, we should have put a 5 there. Oh, so there's a mistake. We mixed those two up. We put 21 and then 5. It should have been 5 and 21, I guess. They say RS2 is 9 and RS1 is 21. We put 21 and then 5. So I think we made a mistake in the load instruction. Or is that the add instruction? That's the add instruction, sorry. Wait there. I disagree because we're doing add X5, X21, X5. I thought RS1 is the first source and RS2 is the second source. So written in assembly language, we have the destination and then RS1 and then RS2, right? So add x5, x21, x5 would be 21 would be the RS1, and the x5 would be the RS2. Oh, but it's RS2, RS1, right? So our RS2 is 5 and our RS1 is 21. So it should actually be 5 and then 21 because it goes in the encoding. RS2 is higher up than RS1. So we did actually mess that up. So there's a mistake in our code. We got that wrong. Let's keep checking here. Func3 should be 0. We got that right. RD should be 9. Of course, ours is 5. And then the opcode is 51. And of course, we didn't write it that way. Although, so they're saying the opcode should be 51. I think I got the wrong opcode written down on that one too. Or no, sorry, I was looking on the wrong line. I got the right opcode. Never mind. Yeah, we've got the correct opcode there. I'm assuming that's 51 in decimal. But yeah, I think we got that right. Next instruction, we have the immediate 1. RS1 is 9, ours is 5, of course. Func3 is 0. RD is 9, and again, ours is 5. And then we have the opcode, which is 19. And again, I'm going to assume we got that right, just eyeballing it. Yeah, we did. Yeah, because that's 16 and then 3, so that's 19. We got that correct. And then the final instruction, we have an immediate 7. I have that correct. Then we have RS2, 9. I put a 5, of course. RS1 should be 10. Yep, I got that right. Func3 should be 3. We got that right. The immediate, the low part of the immediate should be 16. I thought it was 10. Oh, decimal. They put it in decimal. Yeah, we had that right too. I put it in hex. They put it in decimal. Makes sense. Opcode 35. And yeah, I believe we have that correct as well. Yep, because 32 and then 3 is 35. So yeah, the only mistake we made is we mixed up RS2 and RS1 in the add instruction. Other than that, we got it all right. That was the only mistake. And then of course, we chose different registers, but I wouldn't say that's a mistake. If anything, I'd say it's the book's mistake. But again, like I say, I think it's just a case of the calling conventions changing on them. You know, I imagine it takes time to get a book published, and if you change the calling convention when the book is just like getting published, that's just kind of an unfortunate situation. I feel like that's what happened there. But you know, it's not a big deal. We're able to follow along just fine. So yeah, I'm gonna say we got all that correct other than the one little mix-up. The LD instruction is identified by 3, see figure 2.5 in the opcode field and 3 in the func3 field. The base register 10 is specified in the RS1 field, and the destination register 9 is specified in the RD field. The offset to select A indexed by 30, 240 equals 30 times 8, is found in the immediate field. The add instruction that follows is specified with 51 in the opcode field, 0 in the func3 field, and 0 in the func7 field. The 3 register operands, 9, 21, and 9, are found in the RD, RS1, and RS2 fields. The subsequent add I instruction is specified with 19 in the opcode field and 0 in the func3 field. The register operands 9 and 9 are found in the RD and RS1 fields, and the constant addend 1 is found in the immediate field. The SD instruction is identified with 35 in the opcode field and 3 in the funct3 field. The register operands 9 and 10 are found in the RS2 and RS1 fields respectively. The address offset 240 is split across the two immediate fields. Since the upper part of the immediate holds bits 5 and above, we can decompose the offset 240 by dividing by 2 to the 5th. The upper part of the immediate holds the quotient 7 and the lower part holds the remainder 16. Since 240 base 10 equals 000011110000 base 2, the binary equivalent of the decimal form is, and now they're going to actually list the final binary encodings. They did not do the hexadecimal equivalents, but let's take a look here. And the important thing to remember is whenever we put a 5 in our encoding, they're putting a 9. So for us, a binary 5, it's 5 bits, right, for that field in the instruction. And so for us, it was a 0 and then a 0, 1, 0, 1, right? That's binary 5 in 5 bits. And for them, they're doing a 9. So that's actually going to be a 0 and then a 1 and then a 0, 0, 1, right? That would give you a 9 in binary. So that's something we need to keep in mind when we're looking at these encoding differences. So for the immediate, they put 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, and that's exactly what I put here. So that's all correct. And then for RS1, they put 0, 1, 0, 1, 0. We put 0, 1, 0, 0, 1. Or wait, we put 1, 0, 0, 1, 0. Yeah, we put 1, 0, 0, 1, 0, which was did we get that wrong? I think we maybe got that wrong in our translation to binary, because there should be a 10 in that field, right? RS1 should be 10. And it should be 5 bits. Yeah, so I just got that wrong when I was writing it out in binary. It's confusing because you're splitting it up into nibbles, right? But yeah, I got that wrong. So I'm not sure what I was thinking when I did this. If I was looking at the wrong thing or what, because this is just plain wrong. We got this part wrong, but we had it right in the previous step, right? So it was just a case of me failing to translate correctly the fields to the binary. Let's keep going here. We had funct3, which is 0, 1, 1, and that's the 0, 1, 1 we have right here. Okay. Next we have RD 0, 1, 0, 0, 1. And again, I have this wrong. I put 0, 0, 1, 0, 1. Oh, that's that one is because of the 5 versus the 9. So that one's fine. That's just because of the 5 and the 9 difference. And then opcode we have correct. That is what it's supposed to be. Just the 2 low bits set. So yeah, I made a error translating one of the numbers, but other than that, we got that one right. This one's going to be wrong even further because we swapped 2 numbers accidentally. We swapped 2 of the arguments, the RS2 and the RS1. Although technically speaking, the program would still be correct because adding A and B is the same as adding B into A, right? I guess maybe it wouldn't be correct under signed addition though, if one of them is negative. Maybe. Well, no, we're not doing subtraction though, so it would be okay. Like, you can do that. Yeah, I'm pretty sure it would be mathematically okay to have the RS1 and the RS2 swapped in this case. So I think technically, if you want to be technical, I think our instruction is still equivalent. It's not correct in the sense that we didn't translate it correctly, so we did make an error. But I'm just saying that, you know, we'd still get the same result. So not that bad of an error. The first error we made is worse because that's gonna get the wrong register that you're trying to load from. That would be a much worse error. Okay, let's look at this one. So the func7 should be all zeros, which we have. And then of course RS2 and RS1 are going to be wrong. And it's further more confusing in that they have they're using the register 9 and 21. We're using the registers registers 9 and 21. We're using registers 5 and 21, but we have it flipped, so we have 21 and then 5. So let me see here. 1 0 1 0 1. So that's this is like 16 20 21. So yeah, that one looks fine. It's other than it being in the wrong place. And then this one is a 5. Yeah. So again, we just got it in the wrong place. We flipped those 2 in this one. So far, both of them, both instructions we've done so far, we've had errors. So 0% success rate so far, but they're really not logical errors so much. Well, this one kind of is, in that I accidentally flipped it, but it's not that it's just that I think I got confused about which was which. So not a major error. Okay, func3 is all zeros. That's correct. This one 0 1 0 0 1. That's going to be a 9, and ours is going to be a 5. So yeah, we've got the 5 there as expected, and then 0 1 1 0 0 1 1 0 1 1 0 0 1 1. So yeah, that one is completely correct, except I accidentally flipped RS1 and RS2. So, you know, in terms of strictly translating, like I say, we have a 0% success rate. You know, if you're compiling this program and trying to run it, it's not going to run. You know, it's got an error, a pretty major error in the first one with having the register wrong, the wrong number for the register. And then this one is pretty bad. Well, this one's actually not that bad, but it's kind of a lucky coincidence that it's still mathematically the same operation, right? But we flipped the operands, right? We flipped the RS1 and the RS2 accidentally. so not good. On to the third one. We have an immediate 1, so a bunch of zeros followed by a 1. So 4, 8, 9, 10, 11, 12. Yeah, that's correct. And then we have RS1, which again is going to be a 9. So for us, we're expecting a 5. So 0, 0, 1, 0, 1, that's a 5, so that's correct. Next up, we have 0, 0, 0 for funct 3. 0, 0, 0 for funct 3, looks good. Okay, next up, we have RD, which again is 9, so for us, we're expecting a 5. 0, 0, 1, 0, 1, that's a 5, so it looks good. And then finally, we have 0, 0, 1, 0, 0, 1, 0, 0, 1, 1. Yes, that's correct. So that one we actually got completely correct. That's our first instruction that we correctly, compiled down to machine code. So we got that one right. And these ones were close, just a few errors. One error in this instruction, one error in this instruction, and this one's good. So not doing too bad. Okay, next we have 0, 0, 0, 0, 1, 1, 1. Got that. Then we have RS2 is a 9, so we expect a 5. So 0, 0, 1, 0, 1 is a 5. Looks good. RS1 is going to be a 10. So we expect 0, 1, 0, 0, 1. I put 1, 0, 0, 1, 0. So I made that mistake twice. Why was I thinking that's a 10? I made that mistake twice. Like, that's supposed to be x10. I don't know what I was thinking. I did that twice, but yeah, like I say, I don't know what I was thinking in either case there, because that's definitely not 10. What we have there is 17, right? I wrote 17 instead of 10 in both places. This should be a 0 and this should be a 1. This should be a 0 and this should be a 1, right? So yeah, but again, that's just a case of me failing to translate a number to binary correctly. So let's continue. We have 0, 1, 1, 0, 1, 1, then 1 and 4 zeros, 1 and 4 zeros, and then 0, 1, 0, 0, 0, 1, 1, yeah. So again, same mistake in this instruction and this instruction. In both the load and the store, I got it all correct, except that I accidentally translated 10 to binary incorrectly. That instruction I accidentally swapped to arguments, and then that one I got completely correctly. So that's the summary of my attempt. Not bad, but if it were graded, it would be a failing grade. But yeah, I think we get the idea there, and that was some good practice. So I'm glad we did that, even though it's we had our struggles along the way. So, and this is a perfect illustration of why you don't want to be doing machine code by hand, right? Generally, you want to be programming in a much higher level fashion, and you can see, of course, we started with a simple instruction, right? Like this takes a couple seconds to write a line like this, a line of code like this, right? And you don't really need to think hard about what you're typing, right? You know you want the 30th element of A and you want to add H and 1 to it, right? Very simple. But then, you know, getting down to assembly, a little bit harder in that you need to actually think about the proper instruction stream, but that's something you should kind of be doing anyway if you're doing C programming, so this isn't that big of a leap. The bigger leap is, you know, going all the way down to the machine code, and that's if you're doing it by hand, as you saw here, as I just demonstrated, it is an error-prone process, right? There's a lot of room for error in converting numbers between bases, in getting the fields correct, the order of the fields correct, you know, and just typing in the right numbers for, you know, like where they give you, like the opcode needs to be a certain string, a binary string, just getting that typed in correctly. I didn't have that problem here, but that could be a potential source of errors as well. You know, there's a lot of room for error in doing this, and it's pretty long-winded, you know, when you compare this to this, right? You know, the size difference is comparable, and it takes time. It takes a lot of time to start with something like this and actually boil it down to something like this by hand. Yeah, you know, it is a time-consuming process too. So that's a pretty good illustration of why people don't program in machine code these days, as well as why you why you prefer something higher level like this. And also, you know, think about it back in the day when people were programming with punch cards. You know, just imagine, you know, having to have stuff like this on you know, punched into cards and then using that to load your program. Now imagine you've made mistakes like this. You know, that's a pretty painful process, especially if it's like your computer is a big, you know, fills up a room in a university somewhere, and you need to get time allocated, you know, with the university, like, okay, you can use this computer for this amount of time to do your calculations, and so you painstakingly, you know, punch your cards, and then you go to the you know, the computer center, whatever it would be called. I don't know what they would call those. The place where the computer would be at the university, and, you know, load your program with the punch cards, and then see to your dismay that it, you know, fails to run properly. It's your program's wrong, and then you need to, you know, gather up your punch cards and go home and try again, right? And, you know, call up the university and say, okay, I need another time to use the computer. And then, of course, too, with your punch cards, you have the problem of what if you drop them, right? And they're all mixed up now. You have a big stack of them, and now they're all mixed up, and you gotta, you know, order them correctly. And yeah, computing has changed a lot over the years of what it's like, and you know, you definitely don't want that kind of punch card situation, and you don't want to be working with, you know, raw machine code. That's, you know, that's why programmers are writing code like this, not code like this. Good illustration for the day. Let's continue here. I don't think we're gonna finish off the chapter today, although we made the 2.5, I mean. Or wait, never mind, we will. We're pretty close to the end, so we're just gonna power through the rest of it. I know it's a bit of a long episode today, but yeah, like I say, I want to get through all of 2.5, and we've gone a long way in it, so we're just going to finish it off here. Elaboration. RISC-V assembly language programmers aren't forced to use add-I when working with constants. Yeah, that's what I said that too right away. When I translated it to assembly, at first I just put an add, and then when we started lowering it to machine code, I was like, actually, this needs to be an add-I. That's what I was talking about. They're talking about that in the elaboration here. The programmer simply writes add, and the assembler generates the proper opcode and the proper instruction format, depending on whether the operands are all registers, R-type, or if one is a constant, I type. We use the explicit names in RISC-V for the different opcodes and formats as we think it is less confusing when introducing assembly language versus machine language. All right, another elaboration here. Although RISC-V has both add and sub instructions, it does not have a sub-I counterpart to add-I. This is because the immediate field represents a 2's complement integer, so add-I can be used to subtract constants. All right, the desire to keep all instructions the same size conflicts with the desire to have as many registers as possible. Any increase in the number of registers uses up at least one more bit in every registry field of the instruction format. Given these constraints and the design principle that smaller is faster, most instruction sets today have 16 or 32 general purpose registers. And that's a hardware / software interface section there. Okay, figure 2.6 summarizes the portions of RISC-V machine language described in this section. As we shall see in Chapter 4, the similarity of the binary representations of related instructions simplifies hardware design. These similarities are another example of regularity in the RISC-V architecture. So we have R-type instructions. So it's listing out the add, sub, the add-I, the LD, and the SD, like the tables we talked about earlier. But it's showing complete examples for each of them, filling out all the bits of all the fields. So I don't think we need to really go through that. We've already basically covered that pretty well. So I'm just going to skip over the tables here, but I'm going to read the footnote, I guess, the text below the figure. Figure 2.6, RISC-V architecture revealed through section 2.5. The three RISC-V instruction formats so far are R, I, and S. The R-type format has 2 source register operands and 1 destination register operand. The I-type format replaces 1 source register operand with a 12-bit immediate field. The S-type format has 2 source operands and a 12-bit immediate field, but no destination register operand. The S-type immediate field is split into 2 parts, with bits 11 to 5 in the leftmost field and bits 4 to 0 in the second rightmost field. And that's another thing is you see when they write these out, like the ranges of bits, they write them from most significant to least significant, like the ranges. If you have the book, you'll see that what I'm talking about. They write most significant and least before least significant in the ranges of bits when they're talking about like the different fields and stuff, which makes sense because that's how you draw it out, right? You draw the least significant on the right and the most significant on the left. So it makes sense that you have the ranges be most significant on the left and least on the right. But I like to think of it the other way around. When I think of a range of numbers, I think of from least to most in it if I were to write out the range. But I understand why they do it that way, of course. I just thought I'd mention that because here in the text they said bits 11 to 5 and bits 4 to 0, right? They're thinking of it most to least, right? Whereas I would tend to think of the ranges as least to most, going the other way. But hopefully you get what I'm saying there. Let's move on to the big picture. Today's computers are built on 2 key principles. Instructions are represented as numbers. Programs are stored in memory to be read or written, just like data. These principles led to the stored program concept. Its invention let the computing genie out of its bottle. Figure 2.7 shows the power of the concept. Specifically, memory can contain the source code for an editor program, the corresponding compiled machine code, the text that the compiled program is using, and even the compiler that generated the machine code. One consequence of instructions as numbers is that programs are often shipped as files of binary numbers. The commercial implication is that computers can inherit ready-made software provided they are compatible with an existing instruction set. Such binary compatibility often leads industry to align around a small number of instruction set architectures. And industry is adopting RISC-V, so you know that's good news for RISC-V, right? Industry is picking it up. Western Digital, NVIDIA, just to name the first two that pop off the top of my head. So they have a figure here. It's a box that says processor, and then another box that's bigger that says memory. It's like a vertical rectangle. And then in the memory box, there is a bunch of little boxes. They say accounting program machine code, editor program machine code, C compiler machine code, payroll data, book text, source code in C for editor program. So it's just the idea that there's a bunch of stuff in memory, and it can be programs or it can be data, right? It's all stored as data in memory, right? Figure 2.7, the stored program concept. Stored programs allow a computer that performs accounting to become, in the blink of an eye, a computer that helps an author write a book. The switch happens simply by loading memory with programs and data, and then telling the computer to begin executing at a given location in memory. Treating instructions in the same way as data greatly simplifies both the memory hardware and the software of computer systems. Specifically, the memory technology needed for data can also be used for programs, and programs, like compilers for instance, can translate code written in a notation far more convenient for humans into code that the computer can understand. All right, and last but not least here, we have a check yourself for ending up 2.5. What RISC-V instruction does this represent? Choose from one of the four options. All right, so funct7 is 32, rs2 is 9, rs1 is 10, funct3 is 0, rd is 11, and opcode is 51. Okay, well, first of all, before we even look at the options, here are some things we can tell, right? The RD, the rs1, and the rs2 are all registers. This is a R-type instruction, right? So we have three registers that we're operating on, and it's going to be destination register is X11, RS1 is X10, and RS2 is X9. So if we don't see an instruction that's X11 followed by X10 followed by X9 in terms of registers, we know it can't be one of those, right? So let's look at the options here. We have sub, X9, X10, X11. Like I just said, it can't be that because destination comes first, right? And then it's RS1 and RS2. So it's not option 1. Option 2 is add X11, X9, X10. And again, it can't be that because the destination is correct, but they have RS1 and RS2 swapped, like I did in the second instruction here, right? That's what they've done there. They've swapped the RS1 and RS2, so that can't be right. Next, we have sub, X11, X10, and X9. That all lines up correctly. 11 is the destination, RS1 is 10, and RS2 is 9. And then the final option is sub, X11, X9, X10. And again, I said it can't be that, right? Because they swapped RS1 and RS2. So I would say it has to be 3 without even looking up the opcode, without even looking up funct3 and funct7 and seeing what the correct instruction is. Just from the operands, we can tell that it has to be option 3 because that's the only one that has all 3 in the correct locations. So I'm going to say the instruction that they are encoding there is sub, X11, X10, X9. And let's look up the answers to the check yourself here. So just hold on for a moment while I look up the answers to check yourself. 2.5, page 89. The answer is 3, sub x11, x10, x9, and that's what I said. So we got that correct. And that ends section 2.5. So I'm going to end it here. I know it was a long episode, but I'm glad that we made some good progress on the book. I think it's, it's kind of nice to go through an entire section at a time instead of breaking it up across episodes. That's just a lot cleaner. So I kind of like doing that if I can, even though it's, it's a little bit hard in terms of it makes a long episode. So I don't know. If you don't, just leave a comment on the YouTube or message me on Twitter or whatever. I'd love to hear people's feedback of, do you prefer long episodes that go through an entire section at a time, or are you okay with me splitting them up across episodes like I've done in the past? I'd be interested to hear what people prefer. But yeah, next time we are going to continue on with 2.6, but that will be another day. Thank you everyone who tuned in, and thank you also to everyone who watches on the YouTube archive, which is available at risky.tv, and you can follow me at hmn_risky on Twitter to get updates about the series. Thank you also to everyone who supports me on Patreon. It really makes everything I do here possible. I don't believe I have any new shoutouts to give today, but yeah, it's greatly appreciated. It really makes this all possible. If you would like to support this series, you can do so at patreon.risky.tv. I'll see you in the next episode, and stay risky, everyone.